Hello. Good morning, everyone. Welcome to the SPARC Phase 3 workshop on microstructure quantification and their mesoscale and atomistic modeling. In this workshop is from 15th of July to 20th of July, and there are few holidays in between. So in this workshop, we have invited Professor David P. Field, Professor Sinisa Mesarovic, Professor Shomik Banerjee, all of them from Washington State University. Just I would like to give a small brief about each one of them. So Professor David P. Field is a very well-known professor of mechanical and physical metallurgy, and he has done his PhD from Yale University. He has about 30 years of experience. He has been working on plastic deformation of metallic materials, ceramics, microstructure, crystallographic texture, grain boundary engineering. His PhD students, one Alankar is professor in IIT Bombay. There are other PhD students, several places in the world who are in very good positions. He is the chief editor of Materials Characterization Journal. Professor Sinisa DJ Mesarovic is a PhD from Cambridge, Massachusetts. He also have about 30 years of experience, and he has experience in mechanical engineering, phase field modeling, plasticity of crystals, interfaces, diffusion and diffusion creeps, and he has several publications and awards to his credit. He has quite a lot of PhD students in his credit, and I'm keeping it short. Then Professor Shomik Banerjee, he is not present today, but he will be reaching here on 19th, and then his part of the course will also start. So he is associate professor in Washington State University, and he did his PhD from Virginia Tech, Illinois, and MS from Illinois, Chicago. He is a BTech from Jadavpur University. He works on atomistic modeling using molecular dynamic simulation and density function theory. He has authored multiple papers and is a recipient of multiple awards. Just for this, for the inauguration session, I would like to invite Professor Kaushik Vishwas, who is currently the acting head of the Department of Metallurgical and Materials Engineering, to say a word. Say a few words.
Yeah, thank you. So good morning to all of you, Professor David, Professor Sinsina, Professor Siddhartha Dash, all my colleagues, in fact, and good morning all the students. Okay, so regarding this SPARC program, it has been initiated in, as Professor Devala Chakravarti has mentioned, in 2018, and then from that time onwards we have phase 1 and 2. So initially it was some little bit less response, but then this year I think it was really remarkable responses, and we have definitely there are several other faculty colleagues who are also into this program, and this is very good initiative by the Ministry of Human Resources and Development by Government of India to promote very international collaborations, and also to for the students also it will be beneficial for them to go to the foreign countries and have exposures in different laboratories, etc. And also there is a exchange programs like for UK, and we are definitely looking to learn more about particularly the topic which is very pertinent today's because I used to always tell that as a metallurgist we are always a doctor. When anything happens we predict, okay, for not about the life predictions of the human being, but life predictions of the materials, and one of the tool is of course the microstructure, and we can do also post-mortem after failure something, what happens to these materials, how it failed. So all these things we normally as a metallurgist or material scientist we used to do. So and one of the tool is basically the microstructure, and of course many things we cannot do, and that's what the modeling part is there. So you can actually gel together, and I think this workshop will be very fruitful for the students and also for the faculty members to have inside view how we can actually see the microstructures and how we can model it. So it is really, really a good beneficial for the students community as well as for us as well. Regarding the department of metallurgical materials engineering set up in 1954. It's almost as old as IIT Kharagpur itself. So, and we have about 25 plus faculty members right now currently and working in the various fields, and we have a lot of cutting edge technology, laboratories, and maybe if you have some time you can actually go around and visit them. And of course there are other departments as well. If you have some time you can also to visit them as well. And with this note, I will thank all the participation, particularly the student participation, and thank you for coming from so far away from. And thank you, and I wish all the very best to this symposium.
Thank you, Professor Kaushik Vishwas. I would like to call Professor Devalaya Chakraborty, who is Associate Dean R&D of this institute, to show some slides and say something about IIT Kharagpur.
So welcome, sir. So this is mostly for our eminent delegates, Professor Field and Professor Mezarovic and Professor Banerjee, because some of us know about our institute. So just I want to give a glimpse of our institute quickly. So we are a very big institute, and we are literally set up on a prison house. And our progress has been very well connected to the freedom fighting and national development. So this is used to be the Hijli detention camp, where immediately after the independence in 1951, the institute has come up, and 18th August is the foundation day. And then from a very humble beginning, now we have grown to a very large scale. We have more than 16,000 students, 800 faculty, 950 staff, and at any time you will find about 1,200 or more projects, industrially and government-funded projects run in this institute. We are very diverse now because we have 20 departments, 25 centers, 13 schools. You will find engineering and technology, science, then interdisciplinary area including biotechnology, bioscience, healthcare. We have a medical school even now, along with a law school and a management center. So we have this year, our rank has also improved because we climbed 49 rank high. We have certain disadvantages like teacher-student ratio and number of overseas students, overseas faculty. Still, we are doing well. So we have dedicated centers in all the important areas, starting from, say, safety in industry, defense, affordable healthcare. You can have a look here that AI, ML, all the buzzwords now, we have dedicated centers and schools looking after these things. And these are some. There are many more centers. You will find space research. We are very much involved in this, and computation and infrastructure, telecommunication, transportation, and all those things. We have aligned our activities with the recent G20 theme. You may know last year we had G20 summit in New Delhi, and these are all the major action areas. It is decided there, sustainability, environment, and all those things, where we have aligned our activities. And in those important activities, we have immense faculty strength. 30 to about 60, 70 number of faculties are working all these important areas like clean energy and healthcare and manufacturing, sustainability, and all those things. So naturally, we publish a very high number of papers. Last year, we published more than 7,000 papers with very high citation. And we keep track on the technologies that is developed here. So at present, we have a survey continuously we do where we know our technologies which are at the very high TRL level, and we regularly do technology transfer as well. So these are the very important activities of our institute. We have dedicated research parks, one in Rajarhat in Kolkata and one nearby in Gopali. We have a very strong startup culture. You will find a large number of startups from students, and student innovation has gone from this institute. And a significant number of unicorn co-founders in India, means billion-dollar startups, they actually belong to IIT Kharagpur. And we promote our activities, innovation activities among students. So we support different types of robo-soccer and different team kart, which is a racing car competition of the students. So we support all the students' innovations. We have a supercomputer in our campus. Our faculty members regularly present in national level forums. Naturally, our institute is one of the best institutes in the country technologically, and our healthcare domain is also very strong. We have some very important innovations during the COVID time as well for COVID detection. We recently had a very big MOU signed with Ericsson, and several national and international activities. Recently celebrated our Intellectual Property Day, and I think with this, there has been a little bit of dip in projects during the COVID time, naturally, but after that we are we are on our way up. These are the national programs that support SPARC, GAN. You will be happy to know this SPARC, GAN, these are actually conceptualized by IIT Kharagpur and coordinated, nationally coordinated by IIT Kharagpur. So IIT Kharagpur is the national coordinator of these programs. SPARC, you know, is more collaboration, training, as well as research component is there with 28 countries in the world. And as Professor Biswas said, this is the third phase, which is made more focused. GAN is more of a course, training course based, and there are several other things like National Digital Library. IIT Kharagpur is also leading this activity in the country, and there are several national programs that we are significantly involved in. These are the big multinational companies which provide fund to us, project to us, and there are several Indian industries also in this list. And we have a very eminent alumni base, starting from the CEO of Google, Mr. Sundar Pichai, who has been an alumnus of our metallurgy department only. So, and there were several big names from the metallurgy department. Dr. Srikumar Banerjee has been the chairman of National Atomic Energy Commission, and many other important people. So this is what I have to say, and we are always welcome our delegates with warm greetings, and thank you, sir, for visiting the campus. Thank you.
Thank you, Professor Devalaya Chakrabarty, for the nice introduction of the institute. Now I would like to call Professor Siddhartha Das, who is here to say a few words.
Thank you, Professor Biswas. Good morning. I want extend my warm welcome to distinguished visiting professors to this program. Monsoon is yet to start. Hopefully you will see the monsoon torrential rains before you return to US. That will be a remarkable experience for you. And I look forward to learning a lot from both of you in coming days. I'm sure our students will enjoy a lot. Thank you very much.
Thank you, Professor Das. Professor Tapas Bandyopadhyay, if you would like to say something.
Good morning, everybody, distinguished delegates. Thank you for coming long way from US to India, and I think your association will be beneficial for the institute, for the students, for personal benefit to me and others. So I think you will enjoy the stay. As you told, it is like a park. You can see that jackal is running around presently because of disturbance in the ecosystems. It is coming to the localities in the even morning time also. You can see those small jackal or whatever we call as a fox, and you can enjoy just like the ecosystem within this small campus of 1500 acres, where you can see a lot of snakes also and dogs, as street dogs and others. So good inhabitants of a small insect to human beings. So that's the things. So that sometime you can say induced students, a researcher to do research. For that reason, we do research on insect and extract some kinds of say chemicals and other kinds of things. Do research on say plant kingdoms and try to extract some medicinal values out of that. So definitely we have say dedicated animal research laboratory, we have ethical clearance and all kinds of things are there also. So definitely starting from as we consider the microstructural aspects, so understanding the structures in micro level for metal and materials to the others. So definitely that will be interesting, just like say, specifically biomaterial, presently people are working on those areas, and challenge lies on the structure property correlations with reference to that, just like specifically cellulose based or lignocellulose based kinds of things. I think I want to learn all those kinds of things. Thank you for coming us. I hope we will enjoy, your stay will be enjoyable. You should not feel any discomfort within the campus. Somjit generally used to take care of that, and we will try our best to definitely provide you all kinds of facility. Thank you for coming.
Thank you, Tapasda. So I would like to call Professor Shompa Aich to say something and then give the bouquet to our distinguished delegates. Okay.
Hello, good morning everybody. Professor Field, Professor Sinisha, and the students, my colleagues, professor and the students. And this is our, first of all, it's a very hearty welcome to India, in our country. And we are really proud of our country that we are able to brought you here for this type of workshop or conference. You traveled here from far away from USA, and we will try our best to feel you good staying here in India as long as you are staying. Now the workshop has been arranged here. That will be very fruitful, I think, for mainly for basically for the students, because they will have lot of things to learn. The topics we will cover here for microstructure, quantification, which is the backbone of materials characterization, to know the materials signature, what type of materials and all this, and the atomistic related, that mesoscale and atomistic modeling, that is also added advantage, what the students will learn here, because nowadays it is it is kind of must to learn both the things, the experimental as well as the theoretical study, to enhance the knowledge, to have a good publication for the research scholars mainly. So in the modeling also, as you are you incorporated the mesoscale as well as atomistic modeling as far as like density functional, Monte Carlo, molecular dynamics, also phase field modeling. So I think this is a very diverse area for modeling to learn, to cover almost all the items for the modeling and theoretical study, specifically for students. Also, other than students, I think we faculty also are having lack of knowledge in some areas. It's not like that we are faculty here, we know everything. So we will also learn something from you. That's what I think. And we will start with a big hope and good feeling, and we will continue with that, and we will end up with that also. And wish you a very happy stay here. Okay, thank you very much.
So I would request Professor Sampais to give a bouquet to Professor David Field. I would like to like Professor Rice to give bouquet to Professor Sinisa too. And there is no one to take, but it is on video. So I would like to call Professor Siddhartha Rai to say a few words, one word, and then give bouquet to the other professors, as all are our honored chief guests.
Yeah, thank you very much. So again, good morning. Hearty welcome to IIT Kharagpur, to both Professor Phil and Professor Sinisa. So I am sure that this is a great initiative from IIT Kharagpur and Government of India, which is managed by Professor Sundar Vishwas, and it's a very pertinent topic in metallurgy and material science, this microstructure analysis. And I'm pretty sure that the students will learn a lot from this whole workshop. I myself am looking forward to learning from both of you. And I'm sure that, as Professor Tapas Bandapothe just mentioned, that we have a very vast and extensive campus with huge natural life, and I am sure that you will enjoy your stay over here, and which will be remaining in your memory forever. So thank you very much, and have a nice day. Yeah.
So I would request Professor Siddhartha Rai to give bouquet to Professor Siddhartha Das. Kindly give bouquet to Professor Devala Chakravarti. Thank you, Siddhartha. Siddhartha Rai, kindly give bouquet to Professor Kaushik Vishwas. Thank you, Siddhartha. And I would like to give bouquet to Professor Tapas Bandapothe. And to Professor.
Just a minute. Thank you very much, but I would like to hand over it to Professor Songit Vishwas because he is our coordinator. So it is for both of us.
Yes.
Okay. Thank you very much. Yeah, sure.
So with that, it was a warm, nice inauguration. Thank you all for participating in it, and I would thank you in advance for participating in the entire workshop. It will be a good experience, a different way of learning, because how they teach in Washington State University, you get the experience of it. Then it's a combination of, mesoscale simulation with using phase field modeling with microstructures, and in relation to atomistic simulation using molecular dynamics and DFT calculations. And let's see how it goes. And I think it will go very well. So we should go ahead, and we have a high tea outside, and we should go ahead. And that's the end of the inaugural ceremony. Thank you so much. Oh, once again, I missed one thing, and it's a great mistake of mine.
It's upside down. Okay. See myself on the screen, looks strange. I'm waiting for somebody to tell me to go. Go ahead and start? Okay. Dr. Masarovich, Sinisha tells me a lot of things I should do. That is, anyway. Okay, so it's really a pleasure for me to be here, and thank you for the kind inauguration ceremony. I thought to begin with that I would introduce our university as well. So I have slides here. You can't see the slides. What do I do so you can see my slides? Oh, microphone is not working, or oh, it's just not close.
So the screen you have shared on screen, you can see the microphone off. The microphone, can you just switch it on?
That's not on my screen though. I can't do that.
Maybe.
So I'm muted. I have that screen. I have the far screen. I don't have this screen. That looks okay? Okay.
You have here, you see that?
Yes, now
I see.
He's unmuted, so no issues.
Yes.
This is all I see. I don't have the other.
Yes, he will come somewhere there.
Okay. Okay. Now we're good? Okay, now we go. Okay. Okay, so I'll introduce the university to you a little bit of Washington State University. We are in Washington State, which is not Washington, D.C., right? Washington, D.C. is the capital of the country, which is over on the East Coast. So I probably could do a pointer here. How do I do pointer? I'm learning technology. Let's just forward back. This is, there's pointer. Yeah, okay. Yeah, okay. There, thanks for your patience. I get started. Okay, so Washington, D.C. on the East Coast. Here's Washington State up here in the northwest corner, right up against Canada. And if you look at our university, we are divided into 5 campuses. They say 6 because there's a global campus, which is an all-online option. Most of the students, there's about 30,000 students in Washington State University, and almost 25,000 of those are in Pullman. So the other campuses are small campuses, Spokane campus, so this is the Pullman area here. The Spokane campus up here is our medical campus, so that's where medical school is. We have engineering in Pullman and in Tri-Cities and in Vancouver and up here in Everett, and we actually have some engineering over here. There's a naval base in Bremerton where we have a small program, we call it, not a campus, where we teach engineering there as well. So we are in a town called Pullman. It's a very small town. We're about 10 kilometers from the Idaho border, so we're not near the ocean. We're not near the Sound. We're not near Seattle. We are in a very small town. Pullman is about 35,000 people. It's in the middle of the wheat fields. Almost 25,000 of those 35,000 are students. So it's very much a typical college town that we live in. So here's a few images. This one in the middle is a view of part of the campus. We're on a lot of hills, and so you're always walking uphill anywhere you go somewhere. It's always uphill to go someplace, it seems like. Or downhill, like the kids playing in the snow here, like the college students. We don't get a lot of snow like a Minnesota or Michigan or some of these, but we get a little bit of snow we can play in. I like to say this picture over here on the right side, this is the area surrounding Pullman. And Pullman being a very small town, I like to say the picture in the middle is a picture of the campus, and if you turn around and shoot the camera the other way, then you get the picture of the wheat fields. And it's mostly wheat and dry grain. It's non-irrigated farming that happens close to Pullman. Okay, so School of Mechanical Materials Engineering and Institute of Materials Research. Interesting, the font's changed on me, but. So we have degrees, both mechanical engineering and in materials science and engineering. We are divided into schools instead of departments, and that reduces the amount of administrative overhead. So instead of a department chair for mechanical engineering and a department chair for materials science and engineering, we have a school director, and he covers both of those programs. So we offer bachelor's, master's, PhD degrees through the school in all of those. Also, this Institute of Materials Research, I'm the director of that institute. And that is interdisciplinary, so we include chemistry, physics, engineering, Institute of Shock Physics, and try and increase the number of people involved in that. I've listed some major areas of research in mechanical engineering here, just so you can see. One of our big areas is in sports science. So this student here is looking at a baseball bat. So we have a lab that certifies baseball bats for 7 of the 8 associations in the United States that govern baseball. So we have labs and rooms filled with baseballs. We have cannons that will shoot balls at the bats, and we'll see how the bat responds. And I know you don't care, but he did have an Indian student, and he did analyze a cricket bat as well. So he has analyzed some cricket bats. He doesn't certify cricket bats, but he is familiar, and he's played with some cricket bats as well. Very different. It's interesting to hear him talk about those. And he also did, one student worked on hockey sticks. So that's just one of the things that's done in the department that is interesting and unique. We also have a really big lab in cryo hydrogen, so liquid hydrogen and solid hydrogen, making little hydrogen pellets for energy applications, of course. So we have a really big program in that as well. Okay, so go back to this image, which our campus never actually looks like this, right? It's a beautiful image they've set up and staged somehow. But down in this image, the bottom buildings down here, this is where my office is in here, and Sanisha's office is in here when it's not raining through the ceiling on him. Dr. Banerjee's over in this one, so in our labs. So kind of all this is our main engineering complex, and then we have a few engineering buildings in addition to that. And then I could talk a lot about what we do specifically in materials science and engineering. And so I've just kind of listed a few. I'm not going to go through these. You can read some of them. Some of the things that distinguish us, we have a clean room. Not so much for microelectronics manufacture, but we do grow a lot of single crystals, mostly for 2,6 semiconductor compounds, so laser materials or radiation sensor materials, these types of things. And then we'll put electrodes on them and whatever to test these types of things. And so that's something specifically in the Institute that we do. We do, of course, a lot of solid phase metals processing. We don't do extractive metallurgy, so that's something that's missing from our program. We don't do any type of extractive work, but we do a lot of processing. We also have a large program now, this last bullet, in advanced ceramics. And so we have this center called CER3D, that's the Center for Ceramics Discovery, Design, and Development, that's funded through the defense programs in the US, but it's just fundamental research, so it's not applied to anything specifically. And there's a lot of us that are involved in that program as well. Okay. Do have to clear my throat from time to time. Okay, so we're going to start off with crystallography. And I put a disclaimer on at the beginning of all my slides. I've taught these workshops now for about 30 years. And the workshops evolve each time, so I add things, take things away, whatever. But some of the slides I've taught workshops with Stuart Wright and with Matt Now, and with Jerzy Spunar and with Olaf Engler and with a whole bunch of other people. And we've kind of pooled our slides together. So all of these slides that I'm showing you, some of them I didn't make. I probably can't even tell you which ones I've made and which ones I haven't made over the past 30 years. But I give credit to these people, so I'm not plagiarizing and stealing their information. I give them credit, and then we say, okay, we're going to use this stuff and move on. Okay. All right. In addition, electron backscatter diffraction. Now, if some of you know me or you've read my papers, you've probably looked at work I've done in electron backscatter diffraction. So when the technique first was commercialized in 1987, that's when I was a graduate student. And we bought a unit in 1987 to do electron backscatter diffraction. And it wasn't automated. You had to go and you had to take an image, and then you had to do some measurements, and you had to click some buttons, and you had to tell it, okay, this is a 114 zone axis, and that's a 111 zone axis. And then it could come up and tell you what the crystallography of the material was. And it was manual. And so I could do maybe, to begin with, I could do maybe 20 per hour, something like that, 20, 30 measurements per hour, which is much better than if I had to develop the film like they started with, right, a decade before. But then when I finished, I worked at Alcoa for a number of years, aluminum company of America. So aluminum company, they sent me to metallurgy classes and microscopy classes and these types of things. And we realized that with electron backscatter diffraction, we were able to figure out a way to make this automated. And so I left the aluminum company and helped to start a company called TechSem Laboratories to do electron backscatter diffraction work. So I'm going to talk a lot about electron backscatter diffraction. So I'm going to introduce it just briefly here, just in case anybody doesn't know it. Just from people here, just give me a quick indication if you've used EBSD before. So half or so have used it, so you know what I'm talking about. Good. So we're going to do a quick introduction anyway. So this is typically done within a scanning electron microscope. You have a stationary beam that hits on a crystal, you get diffraction that comes out, and you get these nice patterns that form. The specimen's tilted at a high angle, typically 70 degrees or so. And then this tells you about the crystallography of the structure. And then this is just a screen of an actual SEM system. So within the pattern itself, this gives you information of how diffraction occurs within the crystal where your spot is incident. If it's not a spot and it's actually over many grains, then you won't see any pattern, right? It will be clear. It'll be destructive interference. But if you see it, then you can come in here and you can determine exactly what the diffraction bands mean. You can, we call it index the pattern and assign Miller indices, which we're going to go over here. I will tell you what the phase is. So this is a hexagonal pattern compared to a cubic pattern that's being shown here. So here we see iron, we see quartz over here. So it's not hexagonal, it's a trigonal one, but you know, it kind of looks similar. So the quartz is a SiO2 structure versus an iron structure. So that's the information that's in the pattern itself. And it also tells the orientation. So if you look at this and you see the red dot there, that's indicating that the diffraction pattern shown over here is coming from this spot that's on the screen there. And then shows you what the orientation of that crystal is. And then you go to the next spot and you get a different pattern and a different crystal orientation and the next one. And if there's multiple phases, it will be able to tell you that. So you can bounce around and learn about the material. If you do this in an automated way, you will step across in a regular grid. You'll get patterns at each point. Sometimes you'll do EDS at each point. So you can do both chemistry and crystallography at each point. And then you come up with a map that shows the information. Struggling with my throat here a little bit, so. Okay. Actually, Sanisha, could you grab me my backpack quick? I have a cough drop I can grab. It's the one on the floor there behind you. It's the one on the floor behind the couch. Excuse me a minute. Thanks. It's always fine until I start talking too much, and then. This is my magic bag here. Yeah, it's that when I first came here, I ended up getting a little bit of a cold when I first came here, so. So it wasn't ideal, but these are like magic things, so they'll be fine. Purely legal. Magic, but legal. If you need some, you can let me know. Okay. Of course, that's being taped. I shouldn't say that. Okay. So the mapping, EBSD mapping. So what you get is an array of points that has XY positions over a surface, right? Assuming you're working only on a surface. You have XY positions, and you have a knowledge of what the crystal structure is and what its orientation is. You also get a measure of how good the diffraction quality was, if the patterns are really sharp or not sharp. And then you can go in and create images based on that. So these images are not from a standard microscope. They're just standard images. They're just images that we've created. So this one, the grayscale in this, is from how good of a quality the image is, the diffraction image. Colors here are based on what the orientation is, and we're going to talk about all these things, but based on the inverse pole figure color key, the unit triangle. And then we can go in and say, draw a red line if it's 55 to 65 degrees of misorientation between the two neighboring points. And so then you see grain boundaries very nicely, and you get the whole structure. You can go in and analyze what you need to from the microstructure based on those measurements. I'm giving just a little bit of historical overview. We were at the recent ICATOM meeting. I know Gorov was there. I don't know if anybody else made it to that meeting. But in Metz, it was in France a couple of weeks ago. And I gave a lecture, and Bev Hutchinson from Sweden introduced me. And Somjit, don't laugh. What he said was, Dave invented EBSD, so everybody, and I'm like, I didn't invent EBSD, so that took me back a little bit. Anyway, so he said, Kikuchi from Kikuchi Patterns in TEM, he put a film on the back side, so in back reflection mode, or back scattering mode, he saw EBSD patterns in 1928. So about the time electron microscopes were just first getting started, TEMs, first getting started, there was record in a paper of somebody who saw an EBSD pattern. All right, so that's kind of cool. We talked about it a lot in the 50s. Alleman Pashley did, Venables and Harland in the 70s. David Dingley, when I first started using the EBSD in 1987, we all called it the Dingley system. David Dingley was a professor at Bristol University, and he's the one that came up with the computer-assisted indexing, so that's the kind of system I used when I first started. Rizzo in Denmark, Dr. Juel Jensen, Niels Schmid, Niels Krieger Larsen came up with the automated way to do the Huff transform indexing. Thank you, sir. Appreciate it. Joe Michael in Sandia National Lab, he was one that looked at phase ID a lot, but he was really worried about pattern quality, so he was able to figure out how to get really nice quality patterns. Stefan Zephyr and Stu Wright and some others, 3D EBSD when you had FibSim, Stu and Matt, so Wright and Now did the dual scanning with EBSD and EDS together. Mark DeGraff started dictionary indexing for EBSD and also what we call spherical indexing, which I'll get into at some point. The CMOS camera that became very fast, so now we can do thousands of patterns per second instead of 20 per hour like we were doing 35, 37 years ago when I first started doing this. And the latest detector that I have is a low voltage EBSD detector, so I can do EBSD down as low as 3 keV. And we're using a direct electron detector instead of a phosphor screen for that. Okay, so I'm not going to go through these things well. I just kind of threw them in just to say, yep, here's that 1928 EBSD pattern. Right, this is the Kikuchi one that he reported. And you can kind of see some lines in there, right? There's a Kikuchi band in there, so. These are wide angle Kikuchi. Again, this is very similar to what we would get for EBSD. This is the 1950s version. Venables and Harland in the 70s, they're the first one to use the term electron backscatter diffraction patterns. There's a lot of people who have considered whether we should call them backscatter Kikuchi patterns, BK, backscatter Kikuchi diffraction. So many folks, when we first started doing EBSD, would call it BKD, backscatter Kikuchi diffraction, instead of EBSD. Online indexing, David Dingley did that. With the bands was Niels Schmidt in Denmark. Dr. Juel Jensen and Niels again with the automated indexing using Huff transform. With Krieger Larsen, his paper there. And then full automation was first done with Stuart Wright. So this was out of the research group I was working in. But it really came out of Stuart Wright's research thesis and his PhD thesis. So this is really the first automated EBSD image that was created here from Stuart Wright. So I like to show that one sometimes. Okay, so that was kind of, here's what EBSD is, because we're going to talk about it a lot. So that's an introduction if you don't know what it was. So let's go back to the very beginning, and this is talking about crystallography. We're going to define what a unit cell is, so very basic, planes and directions and Miller indices, talking about symmetry and other things in crystallography. We're not going to get deep into group theory or how to really define crystals well, but we're going to have a quick overview just to make sure we're speaking the same language. All right. So, definition of a crystal being written here. You're basically defining an array of points, 3 dimensions, periodic array, a lattice arranged so that each point within the lattice looks the same, right? The surroundings are all the same. The primitive unit cell contains just a single lattice point, right? So if I have an FCC primitive lattice cell, it doesn't look like a cubic. So if I have a face-centered cubic, the primitive cell doesn't look cubic, right? Okay. All right, lattice parameters. We define lattice parameters. So if we have some cell here, which is our primitive unit cell, then we come in, we can define our parameters A, B, and C, which are the lengths of the sides. So these are vectors defining the lengths of the sides. The angles between these, alpha, beta, and gamma, are the other parameters that define the unit cells. So we call these the lattice constants, right? The lattice parameters or the lattice constants. A, B, C, alpha, beta, gamma. And those can be used to define all the structures that we're going to be talking about. Crystal direction is a set of points that lie along a specific line in the crystal. And crystal axes are reference vectors that are used to define the unit cell. All right. Miller indices, right? From your very first material science class ever, assuming you've had these, you've done Miller indices. So you have a lattice or a crystal structure defined by these lattice constants A, B, C. And then you have some direction, and you can define that by these intercepts to the lattices, which are going to be A and B, and then C over 2. So you basically have 1 in A that is coming out, 1 in B that is coming out, and half in C that is coming up. Okay? So you have 1, 1, and a half. Now in Miller index notation, we always use integers, right? So we just take it to the easiest integer. So instead of 1, 1 half, we call it 2, 2, 1. Right? Multiply everything by 2. 1, 1 half becomes 2, 2, 1. So UVW is typically the notation that we'll use for the direction definition, for the Miller indices of a direction, UVW. Now we have these points. So these braces, which are pointy braces versus the square braces. And this is a specific direction. UVW with the pointy braces is a family of directions. So for example, 100 coming along here, or 010 moving along this direction, or 001 moving along this direction. Those definitions are arbitrary. Right? We could look at it from a different viewpoint and they would be different. So these all belong to the same family. They all belong to the same family. 100, 010, the 110s are the same way, right? Here we have a 110, here we have a 101. That's the only two we're showing there. But we have a family of these that are defined by these pointy braces. Square braces is the specific direction. All right, so if we go to something that is not defined easily by A, B, and C, and we need to get the angles involved. So this is hexagonal and trigonal crystal symmetry specifically. We go to a redundant fourth index to define that. And so we will have, instead of A, B, C, we have A1, A2, A3 defined in the plane that are aligned with specific directions in that hexagon. And then the C-axis showing the axis along the hexagon, the hexagonal prism, let's say. So then if you move along one of these directions that is aligned with one of the A directions, A1, A2, A3, we say, well, that is, let me see, I think I'm defining it better on the next slide. Yeah. We're saying, okay, if we move along this blue line, right, and then we project those onto the axes, we say, okay, for this one, we're going up a half and negative half in A1, and we're going up specific A2, direction. So we have minus that we're showing here, and this, if this is the inner hexagon here, is showing the A, then we're going 1.5 positions in negative A1. So we go minus 1.5 there, right? And there we go 1.5 in A2, which we can see on this one. And then 0 in A3 and 0 in C. So this one we would switch to make them integers again, and we'll make them minus 1, 1, 0, 0. Since they're redundant, sometimes instead of calling it UVW, we go to what we call Miller-Bravais indices. And we say UVTW, and T is always a sum of U plus V, negative U plus V. Okay? So this is just how to define Miller indices of directions in hexagonal or trigonal systems. Okay. Okay, we're going to switch to planes. Going to switch to planes, and we're going to do a similar type of a thing where we're going to define these by Miller indices. These now, instead of being called UVW, we call them HKL. And for a specific plane, we have parentheses. And if we have a family, we have these curly braces. Right? So we have 4 different type of parentheses or braces that we put around these, depending on whether we're talking about a direction or a plane, and whether we're talking about a specific plane or direction or a family of planes or directions. Okay. It might be a bad thing, but I teach my students the easy way to remember which ones are for families and which ones are for individuals. Because in families, sometimes you get some pointy situations, and so all of them with points on it are families, right? So you have nice curves for individual ones or the square ones. But families, they have points on them. So your pointy braces, the curly braces with the point here, or for the directions, it's just the pointy braces, the greater than and less than signs. Okay, that's just an aside. All right, so now we're talking about lattice planes. Now, the way we typically would do lattice planes, let me remind myself what's on the next one here. The way we do on these lattice planes is you'll take the plane, you'll find an origin that doesn't go through the plane you're defining, and you use that as a reference. And you say, where does the plane cut through the direction defined by A, B, and C? Okay. So how far is that? So it's A over H, right? Remember, these are HKL. So we're taking A over H, B over K, C over L. So we're basically taking the fraction of this length, and then we're taking the reciprocal of that to give our definition of the plane. Okay. So that's the definition. So it's easy if we say O10, this is A, this is B, this is C, coming like this. It goes all the way to the end. So B over K is 1, right? K is going to be the same length. It's all the way to B, so this is 1. So that's an O10 plane. If we cut it through like this one, we're cutting through A at the 1 position, we're cutting through B at the 1 position, cutting through C at the infinity position, right? So we do the reciprocal of infinity, it goes to 0. So then we have 1, 1, 0, right? And then 1, 1, 1, you can see that it cuts through all the same, and 1, 1, 2. Now all 1, 1, 2 planes are, if we're talking about the specific plane, they're all parallel to each other, right? So you can translate a lattice spacing, and there's your 1, 1, 2 plane. Translate a lattice spacing, there's your 1, 1, 2 plane. And that's important because we like to define the distance between these 1, 1, 2 planes as well, or any of our planes. All right, now if we do this for hexagonal or trigonal systems, it's the same strategy, but now we define these planes as different types of, if we take our hexagonal prism here, it's cutting through only A1 axis, and then negative A3 and negative A1 axes, so A1, A2, A3 positions, and it cuts through here at a half, it cuts through 1 at the other positions. So this would be reciprocals. So instead of half, 1, half, it's 1, 2, 1, right? So 1 bar. If it's the negative position, we say bar on that. Now, do they teach you here to say bar 1 or 1 bar? I've heard both ways, and I say it both ways. Anybody? Bar? Would you call this bar 1, 2, bar 1, O, or would you call it 1 bar 2, 1 bar O? First or second? Bar 1? Okay, so I'll say bar 1. I'm happy with either one. You can convince me either way. Okay. So bar 1, 2, bar 1, O. And then this pyramidal plane, we call it, where it's coming from the edge of the hexagon up through the center. 1, O, bar 1, 1. And you can see that it intercepts all the axes except the A2 axis, which is why we have the 0 there. And then the 1 bar 1, O, O. And so we have a way for doing all the types of lattice planes. All right. Oh. Going back to the EBSD patterns. Each of these bands, we call these Kikuchi bands. Each of these are direct projections of planes. All right. So if I take this plane, let's do one that we've defined here, 110 plane. This plane 110. This is that band. So that black line is actually the direct projection of a 110 plane. Okay? So the geometry of the crystal is going to be seen exactly in the geometry of these EBSD patterns. All right, interplanar spacing. So there's a general equation shown here, interplanar spacing for HKLs based on the lattice constants, ABC, alpha, beta, gamma, and on the HKL plane that is of interest, right? So H squared, K squared, L squared in here. Now if we do these for cubics, of course, ABC are all equal, alpha, beta, gamma are all equal, they're all 90 degrees, and it reduces to a very simple equation like this. It's just A over H squared plus K squared plus L squared square root, right? So if you come from a philosophy like I do, where when I first started working on metals a lot, I worked on aluminum. I wonder why anybody would ever work on anything besides cubic materials, because that's a nice, easy material to work on, right? Now, of course, people do. I have geology friends and all these. Titanium, magnesium, they're great materials to work on, right? Hexagonal. Just gets a little more complicated if you get away from cubic. But it's just math, right? So you can deal with the equations and it works out just fine. Okay. And when I say why would you work with anything besides cubic, I really mean FCC, right? That's what I know best. I know FCC best. So why would you work with anything? Work with steel, that's fine. Just throw some nickel in there, you get FCC, everything's fine. Okay. Kind of a joke, kind of not a joke. Okay. So, interplanar spacing. We have spacing defined here. There's the equation for the cubics. So you see the position between two of these planes. Now, this is a little bit misleading the way I've done this. So we say, let's call that an O2O plane. then the next O2O plane would actually be in a position like this. And so the D-spacing between them would be different than it would be for the O and O planes, for example. So this is actually showing O and O, you know, I have another slide where we're going to talk about this. Let's go through. So there's two-dimensional examples. Look at A and B lattice vectors. They don't have to be the same, it doesn't have to be cubic system. This would be like a tetragonal orthorhombic system, something, they're 90 degrees, but they're not the same length. And so you're moving along a plane that is defined as 1, 1, which means it intercepts A and B at both the end of the lattice vectors. So these are all 1, 1 planes, right? And then we can define the distance between them. Here's a 2, 1 plane. We're going taking the intercept half of B up to A there. So then we have our 2, 1 planes. The spacing is obviously different. 1, 0, and then here's a 1, 5 example where you take 1, 2, 3, 4, 5, and this is coming all the way. And then that spacing between those planes. So the lowest indices have the greatest spacing, right? So if you take the sum of the squares of these, the lower numbers are going to have the largest spacings. So O10 would have a larger lattice spacing than O20, right? That's going to be the smaller lattice spacing. So that's what's being said by this. This is showing the volume of the unit cell. Just some equations, and I think you get these notes, right? If I remember right, I think you'll have access to these notes. I don't know for sure. I think you'll have access to them. If you don't, I can send notes to you if you need it. Okay. Because I've taken these notes from many sources, and I'm happy to share them on too. Okay. All right. Again, sorry for how my text is being shown here. Okay, now we're going to our EBSD patterns and saying the width of these bands is inversely proportional to the D spacing. So if I have a specific lattice, I have a 1, 1, 1 plane, D spacing 2.31, that band is going to be more narrow. You can see the red lines here that correspond to the 1, 1, 1. This is this band along here. It has the largest D spacing, has the smallest diffraction band. Okay? And as you look at a pattern that's a little higher quality pattern, like this one over here, sometimes when you're lucky, you'll see higher order bands here. So you get diffraction from 111, 222, 333. And is it showing up okay? I think at least I can see it on this screen. You can see these different lines that are coming in here, and they're all parallel with each other. They're all being diffracted from the same geometry of planes, so they fall along the same line. But they're 111, 222, 333, right? So, and it would go on to infinity if they didn't have some kind of interference in the diffraction. All right, but the inside one is the 111. That's the lowest lattice spacing. Okay. All right, the concept of a zone axis. Zone axis is simply the line of intersection of two or more planes. If you are a TEM microscopist, a lot of times you talk about a zone axis, and you're talking about which axis your electron beam is aligned with. Your beam comes down, you get spot patterns. If you're looking at a diffraction pattern in TEM, you get the spot patterns. And all of these comes with planes. They come from planes that share that common zone axis. Just the way TEM diffraction works, because of how high the energy is, the electron beam is effectively aligned up in the plane of the diffracting, whatever diffracting plane, and then you get spots coming off of that plane. So we always define a TEM pattern by the zone axis that we're looking at. Right? And really what that means is we have these planes that are diffracting, and that zone axis is shared by those various planes. All right, now this, in crystallography, a lot of times they call this the zone rule, and they call this the Weiss zone law, where you can define the direction, or you can define the plane and direction based on the planes that line up. So if we have an HKL plane 110 and an HKL plane bar 110, then we can figure out what direction the zone axis is by these equations. Now, of course, if you've had, I was going to say freshman math, but for maybe some of you it was high school math, where you learn cross products and dot products. These are just cross products. Any two vectors, and if we say that we have, here's one of the good things about cubic materials. The direction lines up with the HKL plane identification. So if I have a 111 plane, the direction normal to that 111 plane is in the 111 direction. That's not true uniformly for crystals, but for cubics it's true, right? It's a really nice thing about cubics, okay? So if I have a 110 plane and a bar 110 plane, the vectors normal to those are going to be 110 and bar 110. And if I take the cross product of any two vectors, I get a mutually orthogonal third vector. That is this vector here, right? This is just cross product, right? And this one, just a dot product, right? Because if they're 90 degrees from each other, it's going to have a dot product of 0. They don't project onto each other, right? So the zone axis, better, if you're talking about cubics, the zone axis better have a dot product of 0 with all of the planes that are part of that zone axis, right? So let's check. So 002, yep, dot product 0, dot product 0. Okay. So that's all these zone rule and zone law means, right? Check your cross product, check your dot product, okay? So this is showing positions of zone axes on this EBSD pattern. So we talked about these bands being plane projections. That means these busy spots, these interactions, are zone axes, right? So we can define these by direction zone axes. We can define these by planes. So just kind of getting an intuitive feel for what the patterns are include.
The band you are saying, the band, you're saying it is a projection. So it is a projection on the mirror, on the means where the beam is on the phosphorus screen. In which plane?
So the question is specifically about what am I talking about this being a projection? And if you'll have patience with me, I'll do that in the second part of the lecture this morning. Okay? So I'll define that very clearly what I'm talking about. For now, I'm just trying to say these things in crystallography, they're inherent in the patterns themselves. Okay? And if I don't answer it later, then come back and tell me. Okay. All right, so now this is just stuff you get straight out of beginner crystallography book or Wikipedia. If you go to crystals, probably has this kind of thing. So with all the different possible types of symmetries and organization and ABC, alpha, beta, gamma, there are 7 types of crystal systems, and they're listed here, right? I've been calling trigonal, also can be called rhombohedral. It's the same thing with a threefold, with a symmetry on a specific axis where you can rotate it. I haven't talked about symmetries yet. A threefold axis, and just I'll come back and define those again sometime. Okay, so here's the crystal systems, the 7 that are defined. These rotation axes, what we're talking about with these is how many axes are there that you can rotate 2 pi divided by 2, 180 degrees, right, or pi, and get a crystal that looks exactly the same as it did before I rotated it, right? So these are, when we start talking about symmetry, this is what we're talking about. So if we talk about triclinic, there's no symmetry expected in triclinic. Monoclinic, we have 1 symmetric, 2-fold axis. Orthorhombics, we have 3, right? And here you can see the definition specifically. A doesn't equal B, doesn't equal C, but all the angles are 90 degrees, right? So here's the exact definition of the lattice constants. Here's what the symmetries are. It says whether there's a mirror plane or not. It says if there's a center of inversion or not. Center of inversion means that we can take a mirror plane and a translation to make it in a symmetrically equivalent look. Okay. Okay, so the most symmetric system is cubic. Right? It has 6 2-fold axes, 4 3-fold axes. Those are along the body diagonals, the 1-1-1s. We'll talk about more. And 3 4-fold axes, which are the face normals of a cube, right? You can rotate it 90 degrees, it looks the same. All right. Now, this is an important comment here. The system with the highest symmetry in each class is shown, meaning you can have a cubic crystal that doesn't have all these symmetries, right? And the way you do that is you put a little, maybe it's on one of my slides. I don't remember exactly where it is. But you can have a specific arrangement of atoms at each lattice site. It doesn't have to be 1 atom per lattice site. You can have, you can have 2 different atoms. You could have an oxygen atom and an aluminum atom at each lattice site. And if they're arranged in a certain orientation, you rotate it 90 degrees, then that orientation switches. So it's no longer 90 degrees, so it's no longer symmetric, right? So that axis wouldn't exist, but it's still cubic because these are the same, okay? All right, so unit cell symmetry. Usually when I teach this, I have cubes and I'm rotating cubes around and playing with my hands a lot to do this, but I'm just gonna point on the screen here for this one. So when we talk about a point group, we're talking about a set of rotations which when you apply it, it looks exactly the same as it was. So all of the rotations that I can do to an object and make it exactly the same as it was before, physically indistinguishable, that's what the point group is going to be. All right, so for cubics, there are 24 symmetry elements in the point group. So we talked about a 4-fold rotation about a 100 type axis. So you can do that about any of these 3 different axes. You can do 90, 180, 270 degrees. As soon as I do 360 degrees, it's back mathematically to the same position. We don't count that one, okay? So we have 3 here, 3 here, 3 here, which are 4-fold rotations about those axes. So that gives us 9 there, right? And then we have 111 axes. So if you take that body diagonal, rotate it 120 degrees, it takes it to the same position. Or we can rotate it 240. So we have 4 of those axes, 2 of each of those, we have 8 of those. Then we have 110 types, which this is a screwy uh, 110. It should be going straight through here, so sorry about that. So I'm not sure why it's up there, but if I take an axis around that, rotate it 180 degrees, same position, right? Looks exactly the same. Plus we have the 1 is the identity. So the identity is an element of all symmetry groups. So trigonal only has the identity. So if you rotate it 360 degrees, you don't rotate it at all, that's the symmetry for that. And then we can do the same with all our crystal classes, right? So we have hexagonal symmetry, where we have just atoms in these positions, which there's no really any metals that have that structure, right? HCP is what we look at usually, but so we have this, then we have 1 6-fold axis, so the C-axis is a 6-fold axis. And then we have a 180 degree rotation about these axes. So I'm not sure why it says 90, that's a mistake. Right? And we have 6 of those. So that gives us 12 elements of the symmetry group. Okay? So 24 for cubic, we have 12 elements, and hexagonal. And you can go through and say tetragonal, I'm going to have 12. Orthorhombic, I'm going to have, you can go through and figure out what you have for each of them. All right.
One more previous. Like what do those numbers in parentheses indicate? Like right length 2, monoclinic 3.
Okay, so a question was asked about what these numbers in parentheses mean, right? So we've said there's 7 crystal systems. The next slide that I was just about to get to when you asked the question was to talk about the space groups. Rotation groups, the point groups. So that's how many point groups are in each of those types of crystals, right? Right. How many point groups are in each of these? So we have 5 different cubics, for example. Okay. So here we are with the point groups now. So we've talked about 7 crystal systems. We skipped Bravais lattices. I'm sure I have a slide on Bravais lattices, but it seems like I should mention that before. So there are 14 Bravais lattices. And what those mean, I'm just searching quick. I somehow skipped over it somewhere. But what that means is the centering in each of the crystals, right? So we can have a cubic crystal symmetry, or we can have primitive, so there's no centering. We can have an atom in the middle of the cube, so it's a body-centered, or we can have an atom on each face, so it's a face-centered. Okay. So there's 14 of those. So we have 7 crystal systems, 14 Bravais lattices, 32 point groups from these 7 crystal systems. And these are defined by these types of rotations. And they call them by these names: monad, dyad, triad, tetrad, hexad. That's the type of rotations you can do. Monad's just identity. Dyad's a 2-fold axis. Triad's a 3-fold axis, 4-fold axis, 6-fold axis. If you start looking at quasi-crystals, then you get things like 5-fold axes and 7-fold axes, which are kind of fun to play with because you can see the symmetries in the EBSD patterns. So I've included one of those for you in our lab that we start to play with. But for the most part, this is what we have. Okay, so we have rotations, we have reflections, which are mirror planes, and then we have the center of inversion, which is a mirror plane plus a rotation to get it in the symmetrically equivalent position. This is the slide I was looking for when I was saying that you can have a cubic lattice that doesn't have a fourfold axis along 100, for example. So if I take it and rotate it 90 degrees, this yellow and blue atom, now the blue atom will be pointing up instead of pointing to the side. So that's not physically indistinguishable. Still cubic, but it's taken away some symmetry elements, right? So when I say cubic has 24 symmetry elements, that's the most symmetric cubic. BCC has it, simple cubic has it, BCC has it, as long as the motif or the arrangement of atoms at each lattice point isn't switched. Okay. So that's what this is. Atomic arrangements of the lattice points reduce symmetry. We call that motif. And total number of combinations is 32. See if I missed something here. We talked about these types of rotations already for cubics. All right. Now when you look at the EBSD patterns, the symmetry, you know, once you start thinking about the symmetry of the crystals, that's easily seen in symmetry of the patterns. So if we have a pattern here, which happens to be a face-centered cubic type of a pattern with lines that are drawn in there, and it's centered around a 111 axis, you can see in this position is a 211, right? If we rotate 120 degrees about 111, this one rotates over to here, this one rotates down, and now it's a 112 in that position. Rotate it 120 degrees more, it becomes a 121. Right? Now, the way we assign these originally is arbitrary. So we don't know exactly from what the crystal tells us, we don't know what should be specifically 100 or 010, right? Those are assigned arbitrarily. And then we use the mathematics of group theory or of symmetries to take care of all those assumptions. We're assigning it arbitrarily, but then we're saying because of the symmetry, they're all included. Okay. Okay, we're back. Good. Okay, so there's multiple solutions then for all the same patterns. So if I'm saying that we have these types of zone axes or these types of bands, which are, let's say, let's do this one. This is a 110 band. These green ones are 110 type bands. And if the computer assigns this as a 110, then this one it has to assign as something that is going to have the same, can be aligned, can have a 110 that is crossing that plane, right? It can't be parallel to it. You'll have another 110 that will contain a zone axis, and then by those two planes that I assigned, so those are assigned arbitrarily, by those two planes that I assigned, then it gives me what the zone axis must be. And then the rest of them are going to fall in suit. So the first two are assigned arbitrarily, and then the symmetry takes care of all these. But that means I have a whole bunch of different solutions for each pattern. Right, so I have 24 different, for a cubic, I'll have 24 different orientations for each of these for a single pattern. Okay, and then I just have symmetry that takes care of it. All right, so then of course what I've been emphasizing is you see the symmetry in the patterns. There's the 111, which we've looked at. You can see it, there's your 120 degree rotation. Here's one with a 001. 90 degree rotation there. You can see that reasonably well in this one. This one you can't see as well. That's a C-axis in a HCP crystal. And so you have a 60 degree, and then you have another 60 degree up here, which means this point is symmetrically equivalent to that point, which is symmetrically equivalent to that point. Okay? And we'll have some time to play with some of these. All right. Problem is, we have projections of the patterns. I'm not going to talk about it a lot, but it's a distorted image that you're looking at from the phosphor screen, because you're looking at a projection from a point, emanating from a point. And so it's just like how the map of the Earth is represented. You know, we have the globe. So we know the Earth's round, at least most of us know the Earth's round. We know what it looks like on the globe, and we want to represent on the map. So we have to project it somehow. So we can make it so the way we always look at it is if we take it and just plot longitude and latitude as they are squares, then Greenland, which is north of the US, of course, looks really big, right? The island Greenland all of a sudden looks really big just because of how the projection's done. So you get distortions because of the projection. So we have this spherical entity of the pattern coming out. It's coming out in the same, different directions radially, and we're projecting it onto a flat. So we have this, it's called a gnomic projection. So we have some distortion, and we have a tilt of the crystal. So we have the phosphor screen, and we have the crystal like this. So that instead of coming straight out what the poles would be, they're coming and hitting at an angle, and it's being distorted. So if we look at looking straight on at a zone axis, fourfold symmetry axis, you can see, this distance is the same. These are all the same distances. It looks nice and symmetric, right? But now it's tilted 70 degrees like we have in the SEM. Now all of a sudden we say, well, it's symmetric. You can kind of see it, but it's distorted, right? So this is what you actually see. And you just kind of get used to what the distortion is and say, okay, yeah, that's the same, right? That's going to be the same as that one, is the same as that one, is the same as that one. Yeah. All right. Professor Somjit. I don't know what time we started.
Yeah, we started at nearly 10:40 and we finished at 11:40, something like that.
Okay, so is it a good time for a break now? This is where I have the built-in break.
Yes.
Okay.
Yeah. We can have a break.
Okay. You told me to have a break every hour, right?
Yes, yes.
Okay.
They told me.
They told you that?
Yes.
Okay. Thank you. Okay, we're ready? Waiting for the boss. Give me this. You're like the director, you take. Okay. Okay. So now we're going to start talking about diffraction. And we're going to start basic, of course, and hopefully relate everything to what's coming in the future. So most basic in diffraction is Bragg's law. We're not going to derive Bragg's law, we're just giving Bragg's law. Okay, so it is defined here. It's a very easy equation to derive. So we have the wavelength of the incident radiation. All right. Incident wavelength of the incident radiation coming in here, right? We have the wavelength, lambda. We have the diffracting angle, which is the incident angle with the diffracting planes. So here's a set of diffracting planes. D is the interplanar spacing, right, between those planes. So this is dependent on what HKL is. So D, a lot of times, will have the subscript HKL. So we have the radiation coming in, we have the radiation that's diffracted, and it's diffracted only at that specific angle theta, which is defined here, defined in the equation. And this lambda, then the wavelength, D is the D spacing, and then theta is the angle. And basically what you do is say the distance, this lambda distance, has to be some kind of integer value between this path bouncing off the top plane and this path bouncing off the next plane, right? So we have some, they've gone the same distance up to here, and then we have that extra distance that it has to diffract on this bottom plane. And when that extra distance is an integer multiple of the wavelength, then you have just the same wavelength coming out again. You get good constructive interference, and you get good diffraction, right? So that's how it's derived. It's a very simple derivation. So this is Bragg's law that I think we all know. And it's very easy to think about that you have a radiation source coming in, it diffracts, comes back out, you have your detector up there, and you have this, single crystal that we're looking at, basically. Okay. Now for X-ray diffraction, this is just what we call an X-ray pattern, theta 2 theta scan. We're looking at the 2 theta position. So as we scan across the diffracting angles, right, that theta angle, and we scan across a powder or a nice polycrystal sample with random texture, we're going to see peaks every time that D-spacing matches our incident beam angle coming in, right? So as long as that 2 theta matches Bragg's law, we're going to get peaks of diffraction. When we don't, then we just get that background radiation, right? The Bremsstrahlung radiation, whatever we call it. All right. So then we can come in and we can say, based on this crystal structure, we know what Bragg's law is. We know we're going to talk about these extinction rules, which means which planes are going to diffract in which different crystals. Sometimes we call them selection rules, sometimes extinction rules. So which planes actually are going to diffract? And so if we know we have a FCC crystal where if all HKL are odd or all HKL are even, then we're going to get diffraction. Then we can come in and assign what the diffraction is to each of these peaks, right? If we happen to know what crystal structure we have. If we don't know what crystal structure we have, then we can play some games and figure out exactly what crystal structure it is. These patterns are unique for different crystals. Okay, so there's Bragg's law. We know the d-spacing. And then we're just saying here, reflection for 111 planes are going to be at this d value. We know what lambda is based on the energy of the source coming in, and we know what d-spacing of the crystals are. Okay, so if we have this single crystal, we have it rotated like this, we get nice diffraction. If these planes now are at a different orientation, and we have the same angle, they're not going to diffract, right? So we're going to get less intensity up here on the counter, or on the detector. What we do to measure texture, which is what we're going to get to later, we want to see how many different types of orientations are in different types of positions. We can fix this at a given theta value, right? So we have diffraction coming in at a given position, going out at a given position, and then we can rotate the specimen about these alpha and beta angles. We call that a pole figure measurement. But you can consider that if we have this and we rotate this bar up so that it now has these D planes that are parallel again, so the specimen surface is going to be like this, then all of a sudden we get diffraction again, right? All right, so it turns out we have things for that. We have a goniometer, which is just, I don't know what gonio must mean angle or something. I don't know what that is. I'm sure it's Greek and it has a base. If I knew my words, I would know. I think it means angle, measure of an angle, I think is what goniometer means. Anyway, so we have these set up for, this is for reflection mode or transmission mode. So we have a X-ray beam coming in, a counter here, and then we have this this goniometer, or this circle that we can use to align the specimen up in any position. Excuse me a minute again. Okay. All right. So it can be done in reflection mode or in transmission mode. And then this is the result you get. We can't tilt it all the way to 90 degrees so we don't get any information out here. And if you don't know what this is, then basically this is where the specimen's at the normal direction, and then we start tilting the specimen in alpha, we rotate it in beta, and at every point we say how many counts are on our detector. And as you go around, you get more and more counts. We've set up the theta position so that it should be diffracting at a 111, looking at all my 111 planes, for example. And it says, well, I have a lot of 111 planes in this position, and not so much down in these positions, right? All right, we call this a pole plot or a pole figure, and this is just how it's measured using X-ray diffraction. Similar types of measurements can be done for neutrons, any diffracting medium, right? Electron diffraction in the TEM can be done similar to this. It's kind of screwy, you get a little bit of a different type of a view, but it can be done. And with EBSD or with spot patterns, with electron spot patterns, then we're getting single orientation measurements. We can't measure pole figure directly. We basically measure a more complete function than this, and then we back calculate these if we want to see a pole figure. So we'll talk about that coming up. Okay, but this is just measurement by X-ray diffraction of a pole figure. This kind of measurement started in the 1950s, and it's been going on. Still we do X-ray pole figure measurements. Okay. All right. So I want to talk about EBSD and how Bragg's law applies to EBSD. The problem is we have our specimen tilted at 70 degrees, right? That's specimen surface, tilted at 70 degrees. The incident beam comes in, so we say, all right, we have a 20-degree angle between the specimen but the detector's over here somewhere. So it's not the same geometry, right, as X-ray diffraction. This has to be thought of differently than X-ray diffraction. So what happens with electrons? They come in, and then they channel, they scatter all over the place, and you get electrons coming everywhere. And they're going to be coming out of the surface at all angles at the same time. Now, if we assume that those electrons have basically the same energy as when they came in, right? So the incident beam energy is coming in at a specific energy, meaning it has a given wavelength, then that wavelength is going to be the same as it's coming out. So if we look inside and say, here is a few lattice planes, and that's coming out of the surface here, right? So X-rays, or not X-rays. You do have X-rays coming out, but we're not looking at those. The electrons coming out, and they're scattering in all directions at the same time. Some of those are going to happen to be at an angle theta that is the right diffraction angle for that specific set of planes. Now, if these set of planes are rotated at a different angle, there will be electrons at that theta as well. If this d-spacing is different, then it requires a different theta. We have those electrons too, right? So we have electrons satisfying all thetas at the same time. All of them satisfied at the same time. Okay? Good. Now we were talking about this out in the break. These causal cones. So if we have these lattice planes, that's these lines. We have these lattice planes. The beam comes in. We get a diffraction that occurs at theta and theta positive and negative, right? The excess and recess lines kind of thing for Kikuchi diffraction. And they're coming out at these nice cones. And the reason we talk about these cones is because not only are they coming out in a specific direction, you know, it diffracts, comes at this angle, but that same plane is going to diffract all these other angles as well. So if you consider a point source in the middle, then you're going to have diffraction around a whole cone of the same angle, right? Now, if I put a phosphor screen in the way of those cones, and they can detect where the electrons are, then you're going to see this Kikuchi band, where the electrons are diffracting. These are not nice parallel lines, right? A lot of times we look at these EBSD patterns and assume they're all parallel lines. They're actually hyperbola, but they're very flat hyperbola, right? Because you get a plane that intersects a cone, it's a hyperbola. So it's just a very flat hyperbola that's in that position. Okay, so let's do this little animation here. So we have our crystal, have a phosphor screen, we have Bragg's law, we have a diffracting plane, we have an electron beam coming in and it diffracts. We get it diffracting off the top of this blue plane and off the bottom of this blue plane. Now when I talk about the band being a projection of a plane, this is what I'm talking about. Okay, so this was your question, right? The projection. So this is a diffracting plane. So the geometric extension of that plane would come right in between those two hyperbola. Okay, so that is the position of this diffracting plane when it impedes on the phosphor screen here. So this is what the pattern looks like, and if you look at some of these, depending on exactly how you do it, you know, you can tell on this one, for example, this is wider over here than it is down here, right? You can tell that it's kind of, this one is another good one, where you can tell they're hyperbola instead of nice straight lines. So that's how that single plane will diffract, right? So that's just showing one plane. But then we have other planes. So you could have another plane in this position, and it's going to diffract with cones like this. And I tried to draw this, and it just got messy, so I didn't draw it. But you get all that diffraction at the same time. All possible diffracting planes are going to diffract at the same time. And that's why you see this nice pattern. In kind of layman's terms, it can be considered, if you ever look at a nice agriculture plot where you have trees or plants that are aligned in specific rows and they're planted, and you can look down the rows and say, yep, I can see between. But then if you go at an angle, all of a sudden you can see between those rows. You know, they're not really rows anymore, but you can see that angle as well. So that's kind of what's going on here. Anytime those planes can diffract, you're going to get that in 3 dimensions. And so you get a projected view of this 3-dimensional lattice structure of all these electrons coming out. All right. So here's Bragg's law. This is the equation for how energy is related to accelerating potential, right? So this is the quantum version of that law. You just have your Planck's constant here. This is accelerating potential, mass of the electrons, speed of light, right? So you get the wavelength. But the wavelength is inverse to the energy. So you get high energy, you get lower wavelengths, right? And that is why when we talk about electron microscopy a little bit later on, you know, about how the electron microscope works, that's why we get such better resolution on our electron microscope. It's because the radiation, we can have very small wavelengths compared to light, right? All right, so we're looking here at 2 patterns. They look very different. They're exactly the same material. It's a nickel arsenic crystal, which is interesting. This one's at 7 kV. This one is at 50 kV. I don't know exactly the wavelengths those correspond to, but very different wavelengths. Okay. And if you look at kind of the major zone axes, that point is the same as that point. This one here is the same as this one, right? This one in the middle, you can see nice. So all these bands, they all match up. The diffraction, you know, it's following physics like it's supposed to, but they just look like very different patterns. But you're getting the same type of information from them. Okay. So the geometric projection of these, the center of these lines is going to be the same on both patterns. Okay. All right, so structure factor. Which bands exactly are going to be those that are diffracting? So here's the equation for your structure factor. And you can see that this is a function of HKL, function of which plane we're talking about. This confuses us just a little bit, so let me clarify. We were using UVW for a direction. In this equation, this is the only place I'm going to do this, but this is how everybody uses UVW, so we're going to use UVW. In this equation, UVW are the positions of the atoms in the unit cell. right? So the jth atom of the unit cell has a position UVW. It's centered at UVW. So if we're looking at, for example, a face-centered cubic structure, the atoms would be at half-half zero everywhere, right? Because they're going halfway across on the faces and then zero on the other one. So the positions of these atoms, this is going to be sodium chloride, what's being shown here. But all these atom positions are being shown in the unit cell of that rock salt crystal. So here's where they are. Here's how they fall in the equation. So this is UVW for each position of the atom. Okay. So that's how many atoms. J's how many atoms are in the unit cell. This is called the atomic scattering factor. And we'll talk about that. I have one slide on that. And that's just how much that individual element, the atom from that element, how much that's going to scatter. Okay. So this is the atomic scattering factor. Here's an equation for it. And it depends on Z number. It's going to, if you have a heavy element, you're going to get more scattering than if you have a light element, right? So these are raw patterns. This is aluminum. You don't get you don't get a real strong signal from aluminum. Tantalum, a heavier element, you get a stronger signal, right? Now, if we have something like aluminum or tantalum, FCC or BCC, and we calculate this, there's certain places where this value goes to zero, right? Certain HKL for which that goes to zero, which means we'll get no diffraction. So if the structure factor is zero, you're not going to get diffraction. And that leads to these extinction rules or these selection rules. So not all can be observed. Depends on the crystal structure. And then, for example, in BCC crystal, you don't see a 100, but you do see a 200, right? According to the equation, right? So if we look at these rules, if we have a primitive cubic structure or any other type of structure, all HKLs will be seen. That means anything 100, 110, 112, 002, 012, right? All those are going to be seen. For body-centered cubic, H plus K plus L have to be even, right? So 112 will work, but 221 will not work. Okay. For face-centered HKL, they're either going to be all odd or all even. So 111 works, 222 works, 122 doesn't, right? And then we have base-centered or HCP and the selection rules for those. And these are just simple. Usually we'll use the structure factor and say when the structure factor's large, we're going to see the values. We're going to see those, not the values, but we're going to see the diffracting bands. Or in the case of XRD, the peaks. Okay, see if I missed anything on this. All right. So quick on diffraction. So how does this affect pattern quality? This is what we're going to go into now. There's a lot of things we can talk about when we talk about quality of EBSD patterns. And so one of the first things is whether it's deformed crystal or undeformed crystal. Now, why does that matter? One example is if you take a dislocation, this is just a simple edge dislocation in the crystal. All of a sudden you have these planes that aren't in the right positions anymore, right? These atoms aren't in the right position. And so the Bragg condition for diffraction changes locally. And as soon as that changes locally, you get a decrease in diffraction intensity. If it changes enough, you get a complete extinction of diffraction, right? So on this one, it's a nice, clean, pristine crystal, good diffraction. Once it's deformed, less diffraction. And this is just an example of a nickel material that's fully annealed versus one that was deformed. I don't remember how much it was deformed. Specimen preparation, everything was the same. It's just looking at two different parts of the crystal. Just that this one stayed deformed, this one's recrystallized. And this deformed one, since this is recrystallized next to it, this is also probably pretty well recovered, so it's not even as bad as it would be if it hadn't been recovered already, right? All right, so that's the first thing, whether we have deformation in the lattice or not deformation. So what about the conditions of the microscope? This one specifically, we talked already about voltage, so we have 10 kV pattern versus 30 kV pattern. This one is looking at whether we have high vacuum or lower vacuum. So you can do diffraction in these variable pressure SEMs or a low vac mode, but then you get interference from the air molecules in the chamber, right? You don't see those as well. So at high vacuum, you get good diffraction. As the pressure increases, you get worse and worse diffraction, but you still get it, right? It can still be done. So if you're working on a non-conductive sample that you want to use low vac mode for or decrease the vacuum, it can be done. It's just you're sacrificing diffraction quality. And it's not that your crystal's not diffracting. It's diffracting fine. It's just that the electrons getting into your phosphor screen are getting interrupted. Right? Okay, this is a big one. This is a big one. Anybody who's done some EBSD and tried to do automated mapping knows that sample preparation can be a problem. Joe Michael, who I mentioned before, he likes to say, you can take any coin and rub it on your shirt and put it in the SEM and get a diffraction pattern. That's probably true from EBSD. You won't be able to get a good map of the crystal structure. You can probably find a pattern or two in there, but you won't be able to get a good map. You do need good surface condition. This just shows different types of mechanical polishing in this case. This one is just 1200 grit with silicon carbide paper. Not very good diffraction. The reason is you're importing, you're putting in a lot of surface deformation, right? Those dislocations. As soon as you have this heavy grit, you have a lot of dislocations in the surface, a lot of deformation. Go to 1 micron alumina powder or 0.3 micron or 0.05 silicon carbide, or this is colloidal silica suspension. And then, you get better and better as you polish more and more. And we can talk about how that works, but it's just standard metallography, right? Standard metallography. Because when you polish with a 1200 grit, you're going to put some certain scratches in it, but not only the scratches, you're going to have a deformation layer that's about the same depth as those scratches below where so you can end up with a nice mirror finish eventually, but you still have a lot of deformation in there, so you have to get rid of that. So there's a lot of people that talk about specimen prep, but that's one thing. What about if you have a non-conductive sample and you're coating it? That's what this chart is showing. So we have carbon on nickel, we have gold or palladium on nickel, carbon on silicon, gold, palladium on silicon. And you're basically just saying how good the pattern quality is. So this is very low pattern quality. When you get a low Z element, it's not a very good diffractor in the first place. And then you're coating it with something heavy versus coating it with something light, as opposed to looking at nickel that gets pretty good diffraction. It can withstand different types of coatings. Now, of course, if you're doing very low voltage EBSD, you have a problem with coating, right? You need a pristine surface. All right, the other thing that I'm showing here is this surface roughness. So sometimes you can get good diffraction just off a fracture surface, something like this, especially if you have cleavage. But then you start getting these little cleavage planes, these bumps that you'll get in the surface sometimes. And you'll get reasonably diffraction off some, less off others. But what it's showing is you have a different orientation of the place where your beam hits the specimen. So instead of hitting the specimen at 70 degrees tilt with a nice surface, locally your surface is maybe at a 50 degree tilt or at an 80 degree tilt. So you get diffraction either at the top of your phosphor, at the bottom of your phosphor, and it affects your pattern quality a lot, of course. All right. Spatial resolution is a big question a lot about what exactly you can get. If you think of the interaction volume of your electron beam with your specimen, beam comes down, it spreads inside the specimen, and then comes back out. If you're over many grains, let's say you have a nanocrystalline material or microcrystalline material, and you have the beam that's interacting with all of these. So individually, you could potentially have all these patterns, but really you're looking at all of them at the same time. So you get a pattern like this one, right? So that's taking all of these patterns, averaging them, you get this. So a lot of times I'll look at a pattern that my students will show me and they'll say, I'm not getting good diffraction. I'll say, well, I see two patterns in there. Right, here's one orientation, here's the second orientation. This one I'm seeing some bands through here and maybe some down through here. And there might even be a third one, but it's hard to tell what's going on. But a lot of times you can say, I'm getting diffraction from more than one grain. So that means either your grains are too small, or your beam maybe is too wide, maybe you have too large of an aperture, you have too long of a working distance, you have too much beam energy, right? Maybe you decrease your beam energy, maybe you'll have less interaction volume. There's a lot of things you can think about how to do that. So this is kind of the considerations we go through, right? So that's the spot size, which is what your condenser lens current setting is, in addition to those apertures. Probe current, which is the same thing actually. Voltage. Voltage is an interesting consideration because you usually get more clear diffraction if you go to a higher voltage, right? You get a smaller wavelength, but then you get a larger interaction volume. And larger interaction volume gives you less clear, right, diffraction. So it's a trade-off. And then high Z materials, if you have a heavy element, it's better than light elements. Although we've done really nice stuff in things like beryllium and aluminum lithium alloys, you know, you can get pretty good diffraction. It's just painful sometimes. It's not as good as working with stainless steel or tantalum or something like that, nickel. All right. So your beam comes in, it diffracts, it hits a grain boundary. So this is the red orientation, this is the blue orientation, right? Red and blue. And it's giving you information from both grains. And so here's a nice one where if you look at this pattern, you can see elements of both in this convoluted pattern. So we try and figure out how to deconvolute that. And there's a lot of strategies that are done. Usually what will happen is whatever has the most bands, if you're doing Huff indexing, whichever one will give you the most bands. So if you get 4 bands from this one and 3 bands from this, it will assign this orientation to it, right? But it's got a way of doing its voting. It's got a way of analyzing it and knowing, okay, those are bad bands, we'll just ignore those, and we'll analyze these bands from that orientation, okay? All right, here's an example where there's an average grain size of about 70 nanometers, as I recall. I'm looking, his says here 50 nanometers. So about a 50 nanometer average grain size. Some grains were as small as 20 nanometers. You can see the 100 nanometer scale bar. This is platinum. Platinum diffracts really nice, right? Really good diffractor. This was on a deposited film, so it was a sputtered film of platinum. So you didn't have to do any specimen preparation. You didn't have any of those kind of problems of dislocations and stuff you had to worry about. So this is kind of running downhill with the wind at your back, as easy as possible. Yeah, you can get some pretty nice diffraction on really tiny little grains, right? And this is bulk specimen, right? Thin film, I said, but as far as the diffraction is concerned, it's bulk. So it's not like it's a TEM film or something like that. All right. This is something that I never really knew about until I talked with somebody who designed electron optics for JEOL, for Joule microscopes. And this is the interplay of spot size with magnification. So this is just the magnification setting of the SEM. So if you are in spot mode and you have a magnification of 100x, so you can see 2 millimeters, your vibration width is about a 1/4 micron. So that means the beam, instead of being completely steady on a spot, which doesn't happen anyway because it's electrons coming down and being focused, right? And they're circling down, the Borch effect. And so you have all this stuff going on. But you can have a vibration width of about a 1/4 of a micron. So if I'm looking at 20 nanometer grains and I'm trying to do it at 100x, I'm not going to see any diffraction because the electrons aren't at that one spot. They're vibrating back and forth by about a 1/4 micron. If I go to 10,000x, then they're confined to within about 2 nanometers. The same spot mode, right? I put the SEM in spot mode. The only difference is over here I've clicked 10,000x or I've clicked 100x. It's going to be different performance. So if you have small grain material and you're trying to get diffraction, go up to that high magnification, right? Go up to these values where you get this low vibration width. I didn't even know that was a term when I was working with this until I talked to him. So, okay, so that point's clear. I always think of the spot being just a single spot where the electrons are coming in, but it's not. It's vibrating all over the place. Okay. Yes.
Vibration is different from rastering, right?
It's not rastering, right? Right. So this is when it's actually in spot mode, right? So it's not in a selected area mode where it's rastering over a position. It's in spot mode, but the beam itself is kind of rastering anyway, right? It's kind of going over that position. And the diameter of that position is going to change as your magnification goes up. Okay? And it's just the design of electron optics. And he was describing the design to me, which kind of went over my head. So it was a physics thing, right? So I like physics, but I don't really get too excited about particles in a box kind of thing. And so it was that kind of stuff.
Magnification in SEM, we can talk about only when we are scanning. We scan the area, then only we can talk about the magnification.
Okay, there's another question, and I'm doing this for the online people because they don't hear your questions, of course. There's another question that says, magnification only affects the SEM when you're scanning and actually obtaining an image because you're scanning over different regions. So if I say go to 100x, it's going to scan over a bigger region than if I say go to 10,000x and it scans over a smaller region. And that's always what I thought. That's always what I thought, but that's actually not true. You have this vibration width that is also affected by your magnification setting. And so that vibration width, even when you're in spot mode, not scanning, is going to change with your magnification setting. Okay? And you'll see that if you're playing on a material that's got very fine grains, you go to 100x and you put it in spot mode and you say, I don't see anything. Take it to 10,000x or 100,000x, you'll see it. Okay? Okay, so this is just example. This is given materials, so here's two positions. This is at 300x versus at 3000x. This is what the pattern looks at 300x. This is what the patterns look like at 3000x. And it is same patterns, same spots. The only thing different is the magnification setting, right? Okay. All right, so now we have to worry about, well, what setting do we want? You know, what do we need? This is a nice experiment I was doing one time on copper films. And so these copper films, if they get to be about a micron thick and you anneal them, they go from almost all 111 texture to a large grain 100 texture, right? 111 fiber to 100 fiber. And if you don't know what that means, then 2 weeks from now you will, right? We'll talk about it. All right, but you see this scale bar. This is less than 1.5 micron, that scale bar. This scale bar is 60 microns. And what I was trying to do was come down here and say anneal in situ. So I was heating it in situ, and I was trying to see where the nucleus formed for this 100 grains. But to get a decent map down here, I had to have this tiny little region. And so the only thing I ever got, even when I zoomed out a little bit, I could maybe barely get stuff, but then I would get these huge grains growing in from the side. It was a very low probability that I would actually be looking at the area that I needed to look at. So when I'm looking at small grains, I need to have a small step size. I need to have a high magnification to get proper scanning. These large grains, I need to go back out to, to figure out the texture of these things. I have to have a larger step size and a low magnification. So this range in here, I'm getting no EBSD information from at all. This is all just garbage. But I bump up the magnification. This is exactly the same settings. I haven't done anything different other than increase the magnification. I can map these grains out very nicely, right? So you just have to have a strategy that you have to do things in steps sometimes. Sometimes you need large steps, sometimes you need small steps, high mag, low mag. Same with any type of microscopy, right? Same types of strategies that are going to be included. All right. So this is general from EBSD. Let's see if there's something I want to emphasize here. Maybe this bottom thing about diffraction being more complicated than simple scattering events. Bragg's law is a very simplified way to look at what actually happens. And there are a lot of people that have done a lot of books on how EBSD actually occurs from a physics standpoint, how channeling of the electrons happens, and how they get turned back out of the specimen surface. And I'm not talking about that at all, right? Go to Reimer's books or something like that. Dingley has some stuff, but this doesn't really get into the depth of the physics of what's going on. It's more of the mathematics of how we can interpret it. All right, so I have one more kind of module on this part of the lecture because I didn't know where else to put this and I wanted to include it somewhere. So we're going to talk about strain, what happens when you strain material, and can I use EBSD to measure strain? And the answer is, yeah, maybe right? Kind of the answer. So one thing is elastic strain. If we look at the elastic train, elastic train, it's not just a simple value, right? It's a scalar, or it's a tensor quantity. And so you have to go in and look at what happens at each individual band itself. I have some lab exercises that I think we're doing at the end of the week, if I saw the schedule right, but that are involved with some of this, you know, trying to measure some of these things. Very, very difficult to impossible to get any information on this without going to high resolution, which I'll tell you about in just a minute. Plastic strain has some values that we can actually try and get a little bit of information from on dislocation densities, the geometrically necessary part especially. So individual patterns, you look at it. Okay, so we have a pattern, it's not strained. We have one that's strained. All of a sudden, these are at a different lattice spacing than these are. So these are strained bonds, let's say. And then it can affect what our pattern would be. So these strained patterns, you can see some of the bands are going to expand a little bit. You'll see a little bit of a shift. But this is 11%. What's elastic strain? 0.2% is usually how we define it, right? If we don't see a nice yield, we say it's 0.2%. 0.2%, these will look exactly the same, right? Not exactly, but kind of exactly. Okay, if we have a bent crystal, then you have a different orientation at each point. So if you can go in and measure, you could measure orientation at each of these positions. If your diffraction volume includes all of this, it just makes your bands more fuzzy. It goes from being sharp to fuzzy. So you get these diffuse bands instead of the nice sharp bands. So you say, okay, good, we get diffuse bands. Can we come up with a measure of those? There's been a lot of people have tried and haven't come up with any real good measure for plastic strain. Here's another couple of examples. There's a strained pattern, or an unstrained pattern, there's a strained pattern. Can you see any difference? You know, Angus Wilkinson over at Oxford, he's the one that's probably put the most effort into this. He was one of Dingley's students at Bristol when Dingley was developing the EBSD in the first place. And Angus has done a lot of work on this, and we're just not to the point where we say, yes, anything's going to work. Okay. So looking at dislocation effects, if you have these dislocation dipoles, or you have these what we call statistically stored dislocations, you don't get any information other than the diffuse patterns. If you have these boundaries of geometrically necessary dislocations, you'll have a lattice reorientation, and you can measure that. And you can infer what the dislocation content of geometrically necessary, or sometimes we call it the excess dislocation content. How many dislocations are required to make the lattice move from this orientation to this orientation, if it's defined by dislocations in there? And you can calculate that based on EBSD data. All right, statistically stored we're talking to, lower image quality. I'm intrigued how this is changing my fonts. That's always interesting. Yeah, it's interesting. Yeah. Okay, so this is just showing if you have diffraction over this volume and you have some rotated this way and some rotated this way, this is how much it's going to rotate, or how much it's going to change the pattern. So we have the green bonds, the red bonds, the blue bonds, and this is how all the pattern looks. So here's a nice example of something that's completely annealed versus something that's strained a lot. The same material, just strained versus unstrained, the same microscope conditions. So you get these poor quality patterns, and you can see it in your map if you have regions of strained versus unstrained. But quantifying strain is something that we just can't do. Okay, so that's going to move on. Okay. Now, high resolution EBSD. Maybe you've heard of this term, HREBSD. They don't mean high spatial resolution, they mean high angular resolution. So I don't like the term, I usually call it cross-correlation EBSD instead of high-res EBSD. But this is what happens. So you take a pattern that we call a strain-free referenced pattern. Strain-free reference pattern. So if you have a strained material, where do you get a strain-free reference in that strained material? It doesn't exist, right? I consider these to be like the physics problems you have in class where you talk about frictionless bearings and massless springs, right? They don't exist, right? You get these strain-free reference patterns at the same store you get those at. Well, we come up with some estimates, and the way Angus Wilkinson and the others in the UK do it is by looking in a individual grain and finding the pattern that has the least lattice curvature around it and the highest image quality. And they say, okay, that's my strain-free reference.
Dave, welcome to the virtual world. You're now here.
Ah, wow. Nice. I should have wore a dark shirt because I know I'd. Okay. No, I know next time. Nice. Okay. Because I was going like this, and they kept flipping back to me each time I did that. So now I can do whatever I want. Good. Okay, so you take regions in this strain-free, in quotation, strain-free reference, versus in a strained pattern, right? The same region of pattern. And then you say, has this shifted based on this? And you do this cross-correlation, you do this correlation analysis, and you say, okay, it's shifted. And you do that over the entire 20 regions of your pattern, something like that. And you say, okay, well, that's shifted that way, that's shifted that way, this is shifted, so it gives me some kind of shift as a function of position, right? Now this is displacement with position. This is like a deformation gradient, right? I can calculate strains now. The claim is we can go to 10 to the minus 4 strains based on this. So we can actually calculate elastic strains. We can measure locally. Problem is we're doing it based on a strain-free reference pattern that is imaginary. Okay? So that's always the caveat. This is the equations. I'm not going to go through the equations, but it's easy to figure it out. So you go through this and you say, here's how it's shifted, here's the equations, this is my strain. Okay? And I've done quite a lot of work in this area, so I know it kind of works. If you're careful, it works. If you're not careful, it doesn't work. I put somewhere, my last slide was to say there is another group out of BYU, David Fullwood and his group. They have software that's online, that's in GitHub to be able to do this. They use a different strategy for strain-free reference pattern. They calculate a strain-free reference pattern. So you take what's the average orientation, calculate the strain-free reference pattern for that orientation, and then compare each of the strained patterns with the calculated reference pattern. If you talk to each of these groups, they don't like each other very much, right? The people in the UK will say, you can't calculate a strain-free reference pattern because there's all these intricacies of the pattern that make it so you're not going to get the right orientation to begin with. And if you talk to the BYU group, they say there's no such thing as strain-free in a strained sample. The problem is they're both right? Both arguments are right, that that it's not ideal. And so as experimentalists, if you're experimentalists, you know, Sanisha's going to talk to you about modeling. He's resting. He'll talk to you about modeling. And we always say models are never correct, but sometimes they're useful. Experiments are also.
Because it is nearly 1 o'clock.
Yeah, this is my. I'm all done. I'm all done.
No. In the US it is 1 o'clock, so it's for midnight. Because it's 7 hours difference.
Yeah. You're being very gentle. He came from Serbia, so he's you know, it's only 3 hours. It's just my soothing voice. It's my soothing voice. Anyway, no, my last point. Experiments are also incorrect because we don't know all the details, right? In modeling, you know all the details. You put it all in there. It's all in the computer. It's not correct, but you know what you have, right? In experiments, we don't know what we have. We measure it, we assume we know, and we come up with, right? So we need each other is the thing.
Complementary.
We need each other, yes. We're both wrong and we need each other. And that's kind of how I see these techniques. They're both wrong, they can both be useful, all right? So I don't take the side of the fence of one or the other, but they're very much not happy with each other. So as an editor of a journal, I don't send one group of papers to the other group for review. That would be death sentence, so we don't do that. Okay. Do we have any time, Somjit? Do we have any time just generally if anybody has any questions or anything else that we want to?
No, we have time.
Okay.
We can go at least 20 minutes.
20
Can I
minutes
ask
more.
question?
Okay, so I'm done, and I can take questions and maybe start with people online if anybody online has any questions or comments.
Sir, I have a question.
Okay.
Yeah, I'm Sonali from IIT Roorkee.
Hello.
If I have a system, boron carbide, which is not in the EBSD data of the machine, so how can we do such analysis of such systems?
All right, so you don't have a material file is what you're saying, right? You don't know which
Yes.
peaks are going to be diffracting peaks.
Yes.
So then you have to go in and create your own file. So a lot of times you can get that from papers that are online. You can find out somebody who's done diffraction work on boron carbide. You know all the lattice parameters. You can put those in. You can put which planes are going to be the diffracting planes. And then there are some ways. In my next class, I'm going to put my laptop up, and I'll have some software that I can show you what you can do to kind of fit in the right bands. But in general, you take either papers from online or you go to like the JCPDS data file, and it will give you a list of reflecting planes, and you take the lowest index diffracting planes, and you try that first, and then you modify it based on what your patterns are.
Okay. And for measuring residual stresses, we generally use the XRD. So can we have some idea from the EBSD also?
Yes. Yes, that is an area of a lot of ongoing research. So if you do this last technique I said with the high resolution EBSD, you can map out locally where your residual stresses are. So some grain boundaries, maybe you'll have a lot of stress near certain boundaries and not so much near other boundaries. So you can go in and map out residual stress very locally based on EBSD data, with the caveat that you're using a strain-free reference pattern that doesn't exist to be able to give you that information.
Okay. Thank you.
Okay. Anybody else online? Okay, how about here? Any questions? Doubts, yes, I forgot. I forgot we say doubts. Do you have doubts?
Maybe it could be difficult to answer sometimes.
when my Indian students first told me that they have some doubts, to me that meant they didn't believe what I was saying, right? Professor, I have some doubts. I said, what do you mean you have doubts? It's physics. But he meant to me, I would say I have questions, but doubts. I have some doubts. Yes. Right. I doubt that's true.
Yeah, ask something because when we learn after we ask questions.
One question. You said that
Okay.
the surface is not properly polished. In that case, it will have some defects. It will have some defects on the surface. So it affects the EBSD pattern quality. Is it because of the beam penetration or the diffraction on the surface? Is it because of the beam not getting penetrated well inside the crystal, or is because of the diffraction not taking place?
Yeah, so the question is, when you have a prepared surface, sometimes you don't get good diffraction on that surface. You haven't prepared it properly. And the reason for that is you are interrupting the Bragg diffraction condition at the surface. So you're basically moving atoms around. They're not in their Bragg condition, right? They're not in the lattice themselves. So you have a lot of defects. You have vacancies that are induced, dislocations that are induced just from the polishing itself. If you had enough beam intensity to get below that and to diffract back out, if the beam was strong enough, then that wouldn't matter as much. Yeah.
So if the beam intensity can be raised to higher by increasing voltage, it could be possible.
It could be possible. You're always going to get some effects of lower pattern quality. If you don't care about lower pattern quality, you can live with a little bit of distortion on the surface. But typically we try and remove that either with mechanical or electropolishing or chemical etching or something.
But does the defects affect the interplanar spacing? Or
No.
They do not.
No. It has to be measured deeper. Yeah.
They do not.
Okay. Did you have a question? Oh, I thought I saw, maybe there's where I saw the hand. Okay.
Sir, you told about zone rule and zone law.
Yeah?
I want to know in general what is the difference between rule and law.
Okay, so that's a good question. That's what they're called, right? The zone rule and the zone law. So the zone
in general.
law, the zone law is the cross product, and so that's the one that says if I know the planes making up the zone, then I know what the zone axis is. The zone rule is the one that says if I have a zone axis and the planes, then the dot product has to be 0. So the difference between rule and law, it's the same thing, right? That's just how somebody named them. And so I'm just taking whatever names are in the literature. But the difference between the two is one is calculating what the zone axis is, and the other one is ensuring that the calculation was correct. Okay? Anybody else?
This is Sujoy Kot online.
Okay, please.
So you mentioned that the EBSD pattern would be distorted because of the tilt of the sample. Now, does the software correct the distortion of the distortion because of the tilt? Does the software give the corrected version, or is it the distorted version that we get?
Yeah, so the question is a complicated question. The simple part of the question is that it corrects for tilt distortion, okay? So you have the tilt, you tell the beam to move 1 micron down the sample surface, it knows you're tilted how much, and so it's going to move, a 1/3 of a micron, and it's actually 1 micron down your surface. So that's all corrected for in the mapping, right?
Okay.
So as you're doing it, it's corrected, so that shouldn't be a problem. Now, because you're tilted, you also get a trapezoidal distortion, which means that if I have a tilt, I'm focused at this given position, and the beam is scanning, right? From the beam scanning, and it says, I know this is 100 microns, but if I'm scanning over a large region, up at the top region, it's still focused at this position and says 100 microns. So up here, it's only going 80 microns, and down here, it's going 120 microns. So you're introducing a trapezoidal distortion as well. Most EBSD systems don't correct for the trapezoidal distortion. They assume it's small enough if you're doing a smaller area. If you're doing a large area, then it can become significant. So you may have to correct for that. And there are routines online in GitHub. There's some routines that you can go get. But in general, as far as I know, the commercial systems do not correct for trapezoidal distortion.
Thank you very much, sir.
Okay. Yes.
So here in the first slide you talk about low kV EBSD.
Yeah.
So what is the resolution, typical resolution in that?
Oh, das ist eine gute Frage. So also a very good question. So the question for how good the resolution is, these are things we're just trying to figure out. We've done a lot of simulations. The simulations say that we should be able to get to about less than 2 nanometers of interaction, signal from interaction volume by going down under 2 keV. Okay, so if we go under 2 keV. If we're at 30 keV, then we're stuck at about 10 to 15 nanometers. Right, but we can drop it by a factor of almost an order of magnitude if we drop the beam energy by an order of magnitude. Now, experimentally, that is still being proven. We have people working on that. There's a little bit of work. Stefan Zeffer has done some work where he did 30 keV versus 7 keV. But experimentally, the systems that go down to 3 keV are pretty new systems. And so we got one recently, and we're just now figuring out what resolution we can get. We got it specifically to work on ceramic surfaces, actually, because we wanted to look at small grain ceramics without coating them. So that's why we got it. But since I'm a metals person, I just do ceramics because people give me money to do ceramics, right? Because they tell me, do EBSD on this and I'll give you money. I say, okay, I can do that. But my research, my personal research is in metals. And so we're working on, what different materials, how small of grains can you get to at different materials for the lowest voltages we can do. So it's something I'm really interested in the answer of that question as well.
So is it available somewhere? I mean, the commercial machine?
It is. It's called the Clarity. EDAX is the one that sells that. It's called the Clarity. Okay. Mm-hmm. Maybe Super Clarity now. They have 2 versions. So, and it's really expensive. Right?
People actually give you money?
You know how it is being a professor, Sinisha. People give me money, yes, I'll do it, please.
Professor, I have a question, rather doubts, you can tell. Okay. Because so far I have came across this doubt during my study as well as my teaching to now. I have came across 2 terms, like low index planes and high index planes. Preferential growth during solidification. So what does it mean? Low index and high index, is it the Miller indices, low value and high value? If you can little bit explain about that.
Yeah, so that's exactly how I interpret it. Low index planes is the lower values for the Miller indices. And a lot of times I'll just take the sum of the squares of the Miller indices, and then you have a single value that indicates whether it's low index or high index, and it goes 1 up to whatever.
I mean, if there is 2 planes like 110 and 253,
Right.
So 110 is the low index.
Right.
Okay, so larger D spacing, interlamellar
Larger
space.
D spacing, yes.
That is low index. And what does it? What did you tell just now? The squaring and summing that I did not get.
So if you list out all the Miller indices, all the possible planes, 100, 110, 111, 200.
Okay.
And you list them all out, and then usually you put them in order of their sum of the squares. And so 100, sum of the squares is 1.
Yes.
110 is 2. 111 is 3. 200 is 4.
Okay, so it will increase and that will indicate the high index.
Right, as you get higher, those are higher index.
The summation of the square will be more and more for higher and higher index. Right. Okay.
But I don't know the cutoff. Right?
Yeah,
you cut it off at 16. Okay, this is low index, this is high index. That's
okay, there is a relative or comparative.
Right.
Okay, yeah, that will suffice my knowledge, that explanation. Thank you very much.
Good.
So that's a
Oh, I see one.
Sir, in case of heavily deformed steel, like cold rolled steel, why it has a lower confidence index during the EBSD scan? In case of recrystallized sample, it has higher CI value. So a strain is a only reason or something else?
So confidence index is the question. So confidence index in the software you're using has a very specific definition, right? So it is based on how the strategy for getting the solution. And it says, if I look at all the bands that I find in the pattern, and so we haven't covered these kind of questions yet, but I'll try and answer, and then I'll just say we'll talk about indexing later, and it will be more clear, right? Because I do have a lecture on indexing we're going to cover. So the confidence index is saying, okay, the user tells it, let's find 7 bands. But it only needs 3 to find the correct solution. But it takes 3 at a time and then says, with these 3 bands, what's all of the possible solutions I can get from these 3 bands? And so it will give a vote. We call it a vote. I'll give you a vote for these 5 solutions that I can get from these 3 bands. Because we say we're looking at the angles between bands, and we have to give it a tolerance of 3 degrees or 5 degrees or something. So then it takes votes. Now if I find 7 bands, then 7 choose 3, or 7, combinations of 3. There's 35 of those, right? So that's 3 factorial times 4 factorial, right? 7 factorial over 3 times 3 factorial times 4 factorial. Okay, just combinations. So there's 35 possible votes. So if all 7 of those bands are right, then one of my solutions should have 35 votes. Okay, but there's going to be a second one that's going to get some votes also. So the confidence index is the number of first place votes minus the number of second place votes divided by the ideal possible number. Okay, so let's say you have a material that you're not finding the bands very good, so you only really find about 4 or 5 bands, so you get maybe 10 votes. Second solution maybe has 7 or 8 votes, then the confidence will be very low. So one reason is you're not finding the bands very good, right? Another reason might be there are some solutions that are similar to one another, right? So you're finding bands that have solutions that are similar to one another. Now in cold rolled steel, that's not going to be the case. It's going to be pretty distinct. But in some systems, you're going to find, well, this A-axis looks a lot like that C-axis. The bands all overlap except one, and so the confidence is always going to be low. Right? But for something like cold rolled steel that you mentioned, the confidence probably is low because you're not finding the bands very good. The only other option would be it's not calibrated properly. So the angles, the tolerance angles are not fitting very good. So it's got to be either be tolerance or just finding the bands, which could be Huff parameters set up, or it could be specimen preparation, or it could be just that it's rolled too much, right?
Thank you, sir.
Yeah, that's a hard question. There's a lot of possibilities.
So, if the questions are over, then we can end the session for today.
Okay.
We all have the lunch open, and we will have lunch in the department. And next one.
So, give a big hand to Professor Dev for such nice presentation and explanation each and every step. Yes, he deserves it. Big hand.
Thank you, very kind.
Thank you.
Although when I give lectures at my university, people usually don't clap at the end. They usually just get up and leave. No, you're very kind. The voice survives. That was good.
So, to the online participants, today's session is over. Thank you. We will meet tomorrow according to the schedule. Thank you so much. You can log off now. Thank you so much.
If you need your babies put to sleep, put my lecture.